Okay, now with the recording in progress, I say good morning, everyone. Welcome to the Tomita Takesaki mini course that will start today and finish on Thursday. So we have like 4 lectures. Today is meant more to be a little bit like introduction in background. So it's heavily like it's a theory that's having the mathematics and in particular in the mathematical details. So today I will try to give kind of an overview and start with one of the theorems that motivates the study of Tomita Takesaki in several levels, namely the Heschlida theorem. And just before really starting, let me propose something to try to make you also more active into this mini course. So my proposal is that like starting tomorrow, someone give like a 5 to 10 minutes talk of basically why this particular person is interested in Tomita Takesaki modular theory or how it connects with their research or some paper that raises the attention to Tomita Takesaki. So I will ask you to later write to me by email, or I just heard that there is a Slack for the mini courses. So if you like basically volunteering to give us 5 to 10 minutes small speech or talk, or well, it has to be very informal. Yes, just to so you can also interact a little bit more actively with the mini course. So my idea is just to say, oh, okay, I was reading this paper, or in my PhD, in my master, or by research, I came across Tomita Takesaki modular theory, and for that reason, I I got interested, and that's basically why I'm into this mini course. So if you have like, if you're interested in giving this 5 to 10 minutes talk in the beginning of the next lectures, please write to me. And then, okay, if many people volunteer, probably not everybody will have the opportunity. So I will kind of select someone almost randomly so we can interact a little bit more. Okay, so today, as I mentioned, it will be a little bit more background. And one thing that I would like to advertise is that, or basically, physics lives into the very mathematical details. Oftentimes, we hear in physics that, oh, okay, yeah, this is a mathematical pathology. This is something a mathematician would be interested in, but physicists, like in physics, it doesn't really happen. So one of the ideas I would advertise is that physics is very pathological from the mathematical point of view. And that's basically what we are going to, basically see happening in the course of the next lectures. And for that, I will start talking a little bit about like unbounded operators. Yeah, so that's basically one of the main points in Tomita Takesaki. I hope you can always see now this my kind of blackboard that I will use to talk. So I hope everything is working. Um, okay, so what is unbounded? Like about unbounded operators is something that we are somehow familiar, even if you are just studying physics, right? So it's happens all the time. Let me just make like a small kind of like how to say to give you some intuition why one really needs unbounded operator. Imagine you have two operators A and B such that the commutator is basically a multiple of I. Okay, so my claim is that these two operators cannot be buff bounded. So it's a very easy proof of that fact, and that goes basically by looking what happens to a to the power n time, like the commutator between a to the power n and b. And as we all know, a commutator should just be defined as this difference. And allow me to just basically check what's happened by well, by induction. So we know that, okay, the case one is A commutator with B is I. So what happens if I get the square of A with B? And well, that's basically exactly what I wrote above with just 2. And then I will just smartly, let's say, decompose my first A square as A times A, yeah, and then you have B, A, A. And one can recognize that here in the middle, one have like this A times B, which I can rewrite. Or like, okay, so the second one I would not really need to decompose. So it's just a matter of like, okay, of taste. So I can just say, okay, so A times B is the same thing as B times A plus I, and that's exactly what I'm writing here. So it's A, B times A plus I minus BA. And now I can use that again, yeah? So that's A, B, A minus B, A, and then I just keep my I times A to the very end. And here, for this other term, I would do precisely the same. So again, I will say this is, so it's AB, yeah, so that's B, A plus I. And then what I get is, so it's B, A plus I times A minus B, A plus I, A, which is nothing but BA square, and then this BA square cancels out. Oh, I lost a square here. Cancels out with this BA square. So these terms just vanish. And I end up only with this term and this term, which is 2IA. Okay, so it gives you some kind of intuition, yeah, some intuition of what's happening. Okay, so that's the style of the thing didn't match it to the other, so I will just change back to the to A4 so I can have more space. Okay. Okay, that doesn't matter. Okay, it's easier if I just keep with the. Okay, so that gives us some intuition of what should be. So if AB is equal to I, what should be ANB? And that's N times AN minus 1. Yeah, so that's a good guess that happens from here. So here I have that should be 2. I lost the I, sorry. A, yeah, so the 2 comes from the square, yeah, okay. So I and n minus 1. So, okay, so now I have my basis of induction. So by induction, it holds for n. Oops, I identity, which is I a to the power 0. Just for intuition, I just did my case A equals to 2, but now I'm using induction hypothesis to say that A and B is equal to I and A n minus 1. And what I want to prove, so the induction step should be what happens with A n plus 1 with B, and that I will write as A times A n B minus B an minus 1, or plus 1. And well, I'm using exactly the step I just showed you with a square. So that should be a times, and an times b should be b an plus, and then the induction high step, I n a n minus 1 minus b a n plus 1. And now here what I have is a, b, a, n plus, of course, the a and the coefficients commute, so it will be I, n, a, n minus 1, or plus 1, or n, yeah, because that's 1 n here, n minus 1 here, minus b, a, n plus 1. And now I will use the case, well, basically the definition that the commutator between those two is I. So I have uh, B A plus I A N plus I N A N minus B A N. Let's just go. Yep. Plus 1. And that's, of course, B A N plus 1 plus I A n plus I n A n minus B A n plus 1. And then we have cancellations. And here it's same terms of same nature. So n plus 1 A n. Yeah, so it proves that by induction that my formula here is correct. Okay. So from that, I learned that my operators A and B cannot be simultaneously bounded. Why? Because if I have the commutator of these operators, well, this is just the norm of A and B minus A, B A n, which is smaller or equal than, well, the sum of the two. Yeah, so this is just triangular inequality. Okay, but now allow me uh, to say, well, first, we know what is that, yeah, so that should be the norm of n I a to the power n minus 1. Yeah, so that's just the calculation we just finished. And here, of course, I have this an, and I want to have some cancellation. So allow me to write this a to the power n as a to the power n minus 1 times ab plus b a to the power n minus 1. And I will use the fact that for like operators, the norm is submultiplicative. So here I am by contradiction assuming that A and B can be simultaneously bounded. So if they are bounded operators, they should satisfy, well, they both have a norm, and the norm in bounded operators is submultiplicative, which means that this is smaller or equal than the norm of an minus 1 times the norm of a times b. And here, almost the same, I have a norm of b times a times the norm of a n minus 1. And okay, it's now, I hope, clear why I did that. So I can put here just the maximum of these two coefficients, AB of BA times the norm of a n minus 1. And here what I have is exactly n I times the norm of a n minus 1. So the n minus 1 cancels out. Yeah, so I end up with so n, because the norm of I is 1, or the modulus of I is 1. So it's n, the norm of a n minus 1 is smaller or equal than this maximum a b a norm of a n minus 1. And then, okay, this cancels out. So n should be less or equal than the maximum of these two norms, which is clearly impossible. Yeah, so that's so you cannot have all natural numbers to be smaller than some given n. Yeah, so for all n, which means that this commutation relation that we just started implies that either A or B cannot be bounded. Yeah, so one of the two has to be unbounded. So unbounded operators are required by the canonical commutation relations. Let's check something because in the chat. Okay, so it's just a confirmation. So canonical commutation relations require that we need to look to unbounded operators. Okay, so what is an unbounded operator and what type of unbounded operators I want to do? Yeah, so unbounded operators are just too general. Yeah, so that's basically what we call. Okay, there is also a problem with notation of what we call an unbounded operator. So let me start first defining what I will call a linear operator, and later I will tell what is unbounded and what's not bounded, and tell you what's the confusion that often happens with the names. So we are interested in operators A, which goes from some domain. Let's just let's make it a little bit more beautiful. D of A, which should be contained into a Hilbert space. Here I'm always supposing I have a separable Hilbert space. It will make our life much easier, and I don't need anything more general than that. So allow me to just look to linear operators into a Hilbert space. A given one could be 2. Yeah, so that's here I could just look to H1 going to some other space H2. Yeah, so for simplicity, again, I'm supposing my Hilbert space the same, but there is not much difference if I look to two different ones. Okay, so I want D of A, which is the domain of the operator A. Okay, it's not only a subset of the Hilbert space, is a sublinear space. Yeah, so it's a linear subspace. And of course, I want my operator A to be linear, the way we are basically use it with linear algebra. Yeah, that's not much more general than that. Okay, so important things, the domain is a linear subspace of my Hilbert space. And my operator is bounded. Okay, so this, let's say, is the most general type of situation you can have with linear operators. Often we are used to look to situations when D of A is itself a Hilbert space, yeah? So it's a subspace of a Hilbert space, but it not necessarily is closed into the Hilbert space. Yeah, so it means it does not need to be a complete subspace, and therefore not a Hilbert space by itself. Yeah, so just a linear subspace. And that's exactly the type of situation we are interested when you are looking to unbounded operators. So just some nomenclature. A D of A in the Hilbert space into Hilbert space be a linear operator. could be a linear map. Yeah, here operator is just because the space I'm starting and yeah, so the target space and the original, so domain and codomain are the same space. We say that A is densely defined, densely defined if D of A closure is the Hilbert space. Yeah, so that's already tells you that not always you have that D of A is closed. Um, two, and here I'm just well, basically using the things we know. It's bounded if the norm of Ax is smaller or equal than some m norm of x for some, oops, some n bigger than 0, bigger or equal 0, no, could be 0, and for all x in domain of A. Yeah, so that's basically the situation we are used to when you're looking to, well, basic courses in functional analysis, so definitely in linear algebra, in particular in finite dimension, all operators, all linear operators are bounded. All linear maps are bounded more generally. Okay, so those are the, let's say, the the most common and easy situation, and we know that the last situation cannot happen in the situation of canonical commutation relations. Yeah, so that's we just learned in here that it's impossible to have an operator with bounded norm in case it satisfies the canonical commutation relations. Yeah, so in particular, in this case, just so that should be, I hope everybody is familiar with this definition. In this case, we define the norm of the operator as being the supremum over all x with norm less or equal 1 of the norm of a x, which, if you wish, is also equal to the supremum for all x not 0 of the norm of ax divided by the norm of x. Yeah, so that's the usual norm for bounded operators into Hilbert spaces. But as we learn, we cannot have that. That's too much to ask in a physical situation. So again, I'm kind of advertising my point, or like stating my point that physics is a little pathological. If you have canonical commutation relations, let's say the most two common operators in a Hilbert space to define a physical system, yeah, so position and momentum, you cannot have a bounded operator. It requires an unbounded operator. So what's the okay, how to deal with these operators? That's this definition of just saying operator is linear sounds too too broad. Yeah, so that's I need something to work with. I cannot deal with like anything if I don't have continuity. Basically, yes, it's such a basic property. How do I deal? Yeah, so remember, maybe that's a good point. That's I'm not sure if everybody's familiar with. But an operator is bounded if and only if it's continuous. Yeah, so that's one of these basic results in functional analysis. I hope you are familiar with that. But basically telling that canonical commutation relations require the operator to be unbounded is equivalent to say it requires the operator to be discontinuous. Okay? So I will need a more general definition, which is a closed operator. So of course the operator has its domain. I will stop saying that the domain of A is contained into the Hilbert space. That will always be the case unless stated otherwise. And I'll say that an operator A is said to be closed if its graph is closed. So what's the graph of a operator? So it's something that we'll call the G of A, which is, well, basically what in fact defines the operator as a function. Yeah, so it's, somebody works in set theory, say, oh, that's the very definition of the function of the operator. So it's the set of pairs X and A of X, which lie into H Cartesian product with H. Yeah, so pairs such that X is in the domain of H. So this is the definition of the graph. Yeah, so that's the set of these pairs. So that's closed means that this is equal to its closure. Okay, so one can ask, why am I interested into the graph of an operator? And maybe it gets easier if I look what means to the operator to be to have the closed graph. Yeah, so that's if I state that in terms of sequences. So the first thing to notice is that the Cartesian product of two Hilbert spaces is again a Hilbert space, and I'm so maybe putting this as a remark. H is again, oops, or is being considered, maybe just because that's how I see is being considered with the norm or the inner product, doesn't matter. So if I have two vectors, the norm of the pair, I should forget to close the parentheses. The norm of the pair is defined as the square root of the sum of the norms. Yeah. So that makes the like the Cartesian product again a Hilbert space, and I'm looking to the topology with like the closure with this topology or with this norm. Yeah. So a small comment. So we see that G of A is closed if and only if so what happens if I take two sequences so well basically a sequence of pairs but we end up to be two sequences so I get a sequence in the graph of A such that this sequence converge to some point at Y, which is in principle in only the Cartesian product. And then I conclude that X and Y belongs to the graph. Okay, but what does that say? So this is just a basic definition into what happens into a metric space if you have like a set being closed. Yeah, so that means that every sequence in the set that converges to something into the environment space also lies into the set. Yeah, so that's what I just wrote. I just avoided some extra parentheses, maybe. Yeah, so that's a sequence of pairs. So it converges to some point, which is in principle in the ambient space, yeah, so in the Cartesian product. I'm just claiming, so for all sequences such that converge to some point into the to the ambient space, this point also lies into G. This is general for any set to be closed. Just let's see what it says in the case of the graph, in this particular case, so it says the following. If you take the points in the graph, that means that yn has to be a of xn. So points into the graph should be of the form t of xn. Yeah, so that's my yn. And this is a sequence that converts. So I would just avoid saying. So this is a red in the graph. Yeah, so that's points of this sort are in the graph. So if it converges to x and y, then xy is also in the graph, which means the following. So when does this pair converge? And then we see that the pair of, like the sequence of pairs converge to the pair xy if and only if xn converges to x and t of xn converges to y. Then what's the conclusion that we expect is that the point x, y belongs to the graph, which happens if and only if y is the t of x. And maybe more, I forgot to say, but maybe even more important, is that x belongs to the domain of A and y is the t of x. Yeah, so it's basically when I write t of x equals y, I am meaning that is in the domain, but maybe for the first time it's relevant to say that that's basically what say. So an operator is closed, so that would be a proposition which I'm not going to write into in full detail, but an operator A from D of A into is closed if and only if whenever you have whenever xn converges to x and t of xn converges to y, that implies, so again, by writing t of xn, I'm already assuming that xn is in the domain. So it implies that x belongs to the domain of A and t of x is equal to y. So you see that it's very similar to continuity, but it's weaker. Yeah, so that's being continuous is a more demanding request. Yeah, because if you have, so notice that A is continuous, T new require that if xn converges to x, then A of xn converges to A of x, which means that this thing here is convergent and the limiting point is equal to A of x. And here this is a requirement, so I cannot assume that t of xn will converge somewhere just because xn does. Okay? Okay, so one thing that we learned from that is that basically if you have like a operator A that goes from a Hilbert space into a Hilbert space, so this is a theorem. H, well, that is even more general, right? That's could be even for Banach spaces. Yeah, just saying that for Hilbert space, because basically what I'm using be a linear operator or a linear map then A is bounded or here continuous, if and only if G of A is closed. Yeah, so this is the very well-known closed graph theorem. Yeah, so that basically tells you that if you have complete spaces, here I'm saying again, I'm restricting to Hilbert spaces because that's what I will be using, but could even be Banach space. Yeah, so if you have a linear operator between two Banach spaces, well, then if it's continuous, it's closed basically by just this comment I just mentioned above. So this is the easy direction of the if and only if. But if the domain and the codomain are above Banach spaces, the graph being closed also implies the operator to be bounded or continuous, which are two equivalent closures in this situation. Okay, so here what I'm telling you is that having like paying attention to the domain of the operator is very important. Yeah, so that's for unbounded operators, we do want them to not having the domain as the whole space. Yeah, because if the domain is the whole space and you want it to be closed, well, then it will be a red bounded, which we see that does not satisfy requirements, for example, the canonical commutation relations. Yeah? So you have to go to a more general theory by physical requirements, namely the canonical commutation relations. And for that, we need to deal with unbounded operators. If you want to have something similar to continuity, but not as strong as a hypothesis, we have to look to closed operators, and closed operators cannot be defined into a Banach space. Yeah, so that's if they are unbounded, of course, you have closed operators in Hilbert space which are bounded but not unbounded ones. So we need to look basically to operators only defined in some domains, and that's why I introduced this definition with densely defined operators. Yeah, so that's basically, if it's not densely defined, you just basically can restrict to look to the Hilbert space, which is just the closure of the domain. And in the closure of the domain, every operator is densely defined. Yeah? Okay. Other problems that are not so easy to deal with is what happens with the usual operations. Yeah? So we have to be careful because when you sum two unbounded operators or just linear operators, you have to in particular tell what's the domain. Yeah, so and the domain of these two operators will be the intersection of the domains. And well, what it does is obvious. So it's get some vector x and gives you a of x plus lambda b of x. And of course, the same problem with the product. Yeah? So if you look to what's that, it's a little bit more complicated. Those are all x in the Hilbert space, or I can say all x into the domain of B just to save some lines, such that B of x is in the domain of A, which is of course in the Hilbert space, into the Hilbert space. And one of the problems is you can have two densely defined operators, but the intersection of the two domains could only be the null vector. And same thing with this composition. Yeah, so that's it can be complicated. Okay, so due to time restrictions, I cannot go full detail. I'm just kind of creating some awareness. I will try to prove some stuff, but sometimes I will just skip some details because otherwise I cannot do much. So as I mentioned, so here I'm just going some introduction of unbounded operators. I want to also save some time to show you Heschlida. So I will go a little bit more into closed operators, but that would be very important for what we are going to the next three lectures. So that's why I'm going to give you this small overview of unbounded operators. Okay, another issue that we all should be very careful with is the concept of the adjoint of an unbounded operator. For bounded operators, that was quite easy. So for bounded operators, basically what we do is the following. Well, in the end, we want to define the adjoint by some formula. Let's write here the formula is equal to x a of x. And we say, oh yeah, so that defines an operator. Well, yes, for bounded operators, that's true, but why is that true? So what is the vector ax, a star in the vector x? Yeah, so what is in fact this operator? And and the right-hand side is in fact, oh, sorry, I messed it up with one vector. Why? And what allows us to do that is Ries's representation theorem. Yeah, so that's okay. Also some um, confusion about the name. Some people will call this Ries's lemma. Some will call the Ries's representation theorem. I like the name Ries's representation theorem. So what does it say? Is basically it's like, okay, if you have a bounded linear functional into a Hilbert space, it's given by an inner product. Yeah, so that's representation theorem. So what does it say? If you have phi, which is a bounded linear functional into the Hilbert space, so allow me to, oh, it's always a question of notation, yes, if it's a star or if it's a prime. So let's go with prime, yes, because I'm using, the point is that I'm going to have too many primes later, but okay, for this time, allow me to call the continuous dual just H prime. So that means bounded linear functional into the Hilbert space. It means a linear map that goes from the Hilbert space into the field, yeah, which has always to be R or C. Okay. And so what are those if and only if exists some vector z into the Hilbert space such that phi of x is equal to zx for all x into the Hilbert space. Yeah, okay. So if you have a bounded linear functional, there exists a vector z which implements the functional as the inner product. Moreover, the norm of z is equal to the norm of phi. Of course, they have different natures. Yeah, one is a vector, the other is a functional, but the norm is the same. Yeah, I can even say, okay, that this z is unique. Okay, so basically that's what allows us to define what is a star of x. Why? Because I can look to the map. Let's just separate the. So if I look to the map, and then I can look to what is, I will define my phi of, let's see, x, or well, just to, I'm not sure if I want to give a special name. Let's go of y in x is defined by, and that will be y a of x. So this is a bounded linear functional. It is a bounded linear functional because here I'm consider a bounded linear functional. because the modulus of phi y of x, which is just the modulus of the inner product of I ax, is smaller or equal than, well, Cauchy-Schwarz inequality allows me to just write this as a x, which is smaller or equal than y norm of a norm of x. So here you see this is just a constant because y is fixed and a is fixed. And then this representation theorem will say that there exists some unique vector, let me call it z of y or z of phi of y if you prefer, such that um, phi of y is equal to the inner product of z phi of y with x, with the x in here, for all x in the Hilbert space. And well, that's by definition is equal to, so did I put, yeah, so this is by definition equals to this. And here, as I want to obtain, this should be exactly, so that's wish. So that's how I want to define my vector star y with x. So from here, I see how to define what is a star of y is by definition my z of phi in y. Yeah, so that's the unique vector that's guaranteed to exist due to this representation theorem is how I define my adjoint. But you see here, I have to use the fact that A is bounded to guarantee that my operator is bounded, my functional is bounded, and guaranteeing the existence of such a vector. So, well, that already tells you that something different has to happen with unbounded operators. And here, what we have is the following. So if we have an operator A, which is in principle unbounded, yeah, so it's have a domain into a Hilbert space, and I want to say what is A star, I have to first define what is the domain of A star. Yeah, so that's always a problem with unbounded operators. You should start defining where you can calculate your operator. And I will define precisely using the representation theorem for allowing me to say what's the adjoint. So the domain will be all x in the Hilbert space, or if you prefer all y, that's okay. That's just, I'm not keeping the notation from above. But then I have to look to some functional, which is given by the following formula. So you take out y and calculate the vector or the number x, a, y. And if I look to this linear map and I want to say, so here, allow me to just write my wish. So if I want to say, oh, that is equal to a star x, y, which is my wish, then notice that it will be a bounded linear functional just because if you calculate the modulus of this thing, it will be smaller or equal than a star x norm of y. So as a functional, notice that now my variable is y. It's a bounded linear functional. So if this vector is well defined, better that this functional is bounded. And that's how exactly I will define my my domain. Yeah, so it's the domain are all x in the Hilbert space such that this linear map that associates for every y in the domain. So here it's need a little bit more space. In the domain of A is a bounded linear map. Okay, so that's the domain of my operator. So it's the vectors such that that's a bounded linear map. And then what is A star of X is the unique vector such that A star X Y is equal to X A Y for all Y in the domain of A. And what guarantees the existence of this unique vector is, okay, that's an important thing. So if I want to define this vector, it's better to be a unique vector. And here, notice that I told you that's a bounded linear functional between Hilbert spaces are have this vector associated to it. And here I'm defining my functional only into a bound some set D of A. So I need to add some extra information which I forgot, sorry for that. So be a densely defined linear map or linear operator. Then I can define uh, my star of in this way. Why? Because now I have a bounded linear map defined on D of A. So well, basically as I defined it before, so my phi, here I'm changing the name, yeah, so phi of x in y is defined this way, so x, a, y. And by assumption, x is such that this is bounded. Yeah, so that's exactly my domain. I'm calculating a star, I want to say, in the domain. But that's only defined in D of A into C or R, but mostly to C. So I cannot in principle use the representation theorem, apart from the fact that since it is bounded, I can extend it to the closure. Yeah, so admits a bounded extension. Yeah, so that's basically saying that if you have a continuous linear map defined into a linear space, you can extend it to the closure. That means a bounded extension. I hate these things to write. Extension. And then I will, of course, call it the same name. So it's well, oops. Hi. So just this abuse of notation, I will say that it will go from H to C. So notice here that I'm assuming that D of A is dense. So I can extend it to the closure, but the closure is the whole Hilbert space. Yeah, so that is D of A bar into the Hilbert space. So that's basically this thing. And by his representation theorem, so by, oops, he theorem, I will have a unique vector such that there exists a unique Z into the Hilbert space such that phi of x, here of course I'm meaning the extension, but it's the same, so x y is equal to z y, and we define A star of x equals to z. Yeah, so notice that this z depends on the vector x because phi of x depends on x. So that's if you want to be very precise, so it's a z that depends on x. Okay, so the domain of my adjoint depends on, of course, the domain and everything. Yeah, so for example, I could take the domain of A to be only the null vector, and then okay, that's not densely defined. Remember, that's problem is can also happen that the A star has only the null vector as the domain, and also um, it can happen that it's not densely defined. Yeah, so it's not always true that A star is densely defined just because A is densely defined. Okay, so due to having not so much time, allow me to write some propositions that you can check later. So if A into the Hilbert space is a densely defined operator, A star is closed. Yeah, so that's the first interesting consequence. The star of the star of a densely defined operator is always a closed operator. Yeah, so please do that as some kind of trying exercise that you understand how things works. Um, and another thing is that if A star is also densely defined, A is contained in A star, A star star. Yeah, so the double star. In fact, even more is defined. So I can just give you a small definition and just some syllables are missing. Definition. So we say that an operator A in Hilbert space is closable if it admits a closed extension. In that case, or in which case we defined a bar, yeah, so that's the closure of the operator to be the smallest closed extension of A. Yeah, so not every operator is closable. Yeah, so it's something that does not come for free. So you have operators that are simply not closable. They don't admit closed extensions. But if it admits a closed extension, we can look to the smallest closed extension. And that's called the closure of the operator. Yeah, so that's the operator is called closable. And this A bar is the closure. And another thing that's connected exactly to what I wrote above. An operator is closable if and only if Let's bring it a little down. If and only if A star is densely defined, and in this case, what is the closure is precisely the operator that we see above. Yeah, so the star star is the closure. Yeah, so that's, as I mentioned, the star of any densely defined operator is closed. So since I'm assuming that A star is densely defined, you can calculate the star. It's in particular, it is the closed extension, therefore, of A because of what I told you above. Yeah, so this inclusion. By the way, I hope that this symbol of the inclusion is well defined. So those are not sets, they are operators. And what I mean with this is that the operator on the right is an extension of the operator on the left, meaning that the domain of the operator on the right is bigger, and in the domain of the smaller, the two operators coincide. Yeah, so that's just to be 100% sure we are in the same page. Uh, okay, so if that joint is densely defined, then the closure is the double adjoint. Yeah, so that's something quite magical. Another thing that I will just pointed out, it's another definition, but you should always all be kind of familiar, is what does it mean to an operator to be self-adjoint? So please don't confuse self-adjoint operators with symmetric ones. Yeah, so say that an operator is self-adjoint means that the domain of A is equal to the domain of A star, and AX is equal to A star X for all X into either. Yeah, so let's say they are the same. Not to be confused with an operator to be symmetric, which means that D of A is just a subset of this other set. And of course, when I say that one is an extension, I just say that this is true in the domain only of the smaller. Yeah, so these two things are different. Okay, so the first one is, as one can imagine, means that the operator is self-adjoint. The second means that the operator is symmetric. Just to give you some, I will use later some spectral, or some functional calculus and spectral theory, even though I'm not going to define it in full detail because, well, it's just one preparatory lecture for what's about to come. Um, but okay, for self-adjoint operators, I can claim that the spectrum is real. For the symmetric ones, it's not true. Yeah, okay, so in fact, it's a symmetric operator which is not self-adjoint will have like either the upper half plane or the lower complex half plane into its spectrum. Yeah, so that's it is a very different situation in terms of spectrum of these two operators. Okay, so the last thing I want to do, and I will have to be a little bit fast if I want to cover also Heschlida and keep my plans for today, is talking about the polar decomposition of a closed operator. Oops. So polar decomposition, you all know what it should be. It's inspired by complex numbers. Huh? So if you have a z in the complex number, I can write z as the modulus of z times the phase, sometimes called the argument of z. Yeah, so you find some phase such that this decomposition is true. And notice that I can, well, allow me to just make one small comment because that's also maybe a good point to introduce the real and imaginary part, the composition. Yeah, I can just write z as the real part of z plus I, the imaginary part of z. Yeah, so that's non-surprising claims, in particular um, for complex numbers, but for operators it's a little different, but it's still true. And what I mean is the following. So I wanted to define a way of writing operators in these two ways. Yeah, so I didn't talk much about the background that we are going to discuss. I will introduce it before Rechlida. But what I want to say in here is the following. So if you have an operator A, and for now okay, so it's I'm thinking operators in bounded operators in the Hilbert space. I can write my operator A as the real part, and by the real part I mean the self-adjoint part. Yeah, so that's notice the similarity between, and that's something that will be present quite heavily in the whole course of these lectures. So I can, of course, look to what is, allow me to define the adjoint as the star, or to denote it by the star. And that's just the operator that gets z and flips its imaginary part. Yeah, it flips the sign of the imaginary part. So I will do the same thing with my operator. So if I have an operator in B of H, I can do the following. So maybe let's start with the easy one, which is the second, so the Cartesian or the real imaginary part. I can write my operator as always a sum of two self-adjoint ones, namely, here we all know what's the real part, yeah? So that's the real part is just z plus, oh sorry, z is equal to z plus z star over 2, and I will do the same thing here. So just define as a plus a star over 2. Sorry. And I can do the same thing with the imaginary part, yeah, which will be just a minus a star divided by 2i. And we see that these two operators are bounded. Sorry, these two operators are self-adjoint here. I'm supposing they are bounded from the beginning. Okay, so that's just for simplicity in particular, because I'm going to do that mostly with bounded operators. But how about the polar decomposition? Yeah, so that's I'm interested into something of that sort. And here we see that it's something, so just for intuition. So A, we kind of know what is it. Yeah, so it's the modulus of the complex number. So it should be something very similar to the modulus of the complex number. So allow me to already like anticipate what I mean. So what is the modulus of the complex number? It should be the square root of the product of the star by the operator. And this is my definition. And of course, I want to give you a definition of what is that. Yeah, so that's, again, it does not come for free. And second, I want to tell what is the phase. And for that, I will say that A is equal to some U times modulus of A, where U is a partial isometry. So what's a partial isometry? Of course, it's what plays the role of the phase of the complex number. But by definition, a partial isometry is, sorry. Oops. Oh, no, it was correct, sorry. So it's U star U is a projection. Okay, so how to show that such a so I wanted to convince you that such a decomposition exists, and I hope not to take long because I still want to do a little bit more today. It's we always overestimate how much we can do in 2 hours. Okay, so basically the result will be the following. Yeah, so that's or could be a theorem. Yeah, so this is a okay. I will not write the what's the domain. Yeah, so it's at A, B, A densely defined closed operator. Could be between two Hilbert spaces, don't need to be the same. Then there exists a partial isometry. Partial isometry. Isometry U such that so the kernel of the operator A orthogonal, which is equal to the range of A star closure, which is also equal to the range of modulus of A closure is the initial space of U. So what's the initial space? So remember that I told you that U star U is a projection. So it also implies that U star is a projection. So the first one is called the initial projection. Yeah, so it's the projection exactly into, in this case, into the range of A star. Yeah, so this U star U is the projection into the closure of the range. Yeah, so the closure of the range is a closed subspace of my Hilbert space. Therefore, there exists an orthogonal projection associated to it, and the orthogonal projection is precisely U star U. Yeah, so that's what I mean by it is the initial space of U. Yeah, so that's the space where I'm taking the initial projection, space of U. And well, basically the opposite is the final space, kernel of A star orthogonal, which is the range of A bar is the final. Sorry, let's just erase this end because there is a third property that comes. True. Final is the initial space. This kernel is the final space. And my operator A is nothing but U modulus of A as I claimed. Yeah. So what I'm saying is like this decomposition exists for some partial isometry, and modulus of A, as I mentioned, is defined as the closure of the operator. Sorry, is defined as the square root of this operator. So here I'm hiding some facts which I will not have time to go into full detail, but it's important to know is that A star A is a positive operator. Yeah, so it's self-adjoint in particular. Notice that it's not obvious from the very beginning, okay? Yeah, because okay, you know that A star A is has as an extension, uh, it's like it's a star, but it's not true that it's like not that obvious initially that it is self-adjoint, but it's in fact is. And more than that, it's positive. Therefore, I can use functional calculus for unbounded operators. So notice here that I'm just saying it's a densely defined closed operator. But okay, so it's closed and self-adjoint, or self-adjoint implies closed in particular. But it's a positive operator. I can take the square root, and that's how I define this one. And from that, I can conclude that I can get my operator as the decomposition that looks like a polar one. So let me just give you an idea of the proof. So I'm not going to go into full detail again because I still want to do a little bit more today. But U is defined, let's say, in the usual way. Yeah. So the natural kind of way of defining it is by forcing the operator to be precisely what you need. Yeah. So that's so define. So allow me to just for now using some kind of like hat just to differentiate one U from the other, even though they look very similar. So I will say that I get an operator like U hat, and okay, so let's go in parts. So I will have to say what's the domain of this operator, but what I'm defining is the following. It will take the operator, a vector of the form modulus of A calculated in X, and will give you A in X. Yeah, so notice that what I'm saying is basically, so let me do some sketching here. If I get my U hat and I calculate in a vector of the form modulus of A in X, it should give me A of X, which is exactly what I want, apart from the fact that I haven't gone through much details. Yeah, so that's basically I'm forcing the conclusion I want. Okay, but then I'm defining my operator only into vectors which are of the form modulus of A calculated in X. So this operator just go from the range of modulus of A into my Hilbert space. Yeah, so that's the first thing I have to be careful about. So I haven't defined my operator in the full space, but only into some subset. Okay, so now I want very much that this to be well, a partial isometry. That's the first thing. And in particular, if it's a partial isometry, it must have modulus 1. Yeah, just for mentioning. But okay, so let's go in parts. Yeah, so that's basically what is basically the range of A and infinity. Well, it's like what's the relation between the range of modulus of A, range of A? Does this operator preserve norms? So notice that being a partial isometry means it looks like almost a unitary operator. Yeah. So if U star U and U star are the identity, I would conclude that this is a unitary operator. So it basically it's called partial isometry because it's an isometry. Yeah. So it's preserved the norm, but only in the orthogonal of its kernel. Yeah, so it gives you 0 in the orthogonal of the projection u star u, but otherwise it preserves norm. Okay, so that's basically what I have to check. And so many things I have to say. First is this operator is well defined. Second, what's the relation of the ranges? What's the relation of the norms? Does it really keeps the norm into the correct space and so on? So the important thing to notice is what is the norm of ax squared. And of course, by definition, it is the inner product between a of x and a of x, which I can write as a star a x with x, which I also identify as the modulus of a square. Yeah, so remember the square root of this thing here is the modulus of a, so this is exactly the modulus square, which is, of course, again, modulus of x, which is the norm of modulus of a in x squared. So this vector here and this vector here, so this is the second, so maybe let me just try to use some colors. So this vector in here, oops, this is the one down here, and this vector in here have the same norm. So this u hat preserves the norm. Yeah, so that's so that tells me. So that's the first conclusion. Norm of u of a vector a x is equal to the norm, well, by definition of a x, which is equal to the norm of modulus of a, oops, x. So in particular, it preserves norms. Yeah, so it is an isometry, and therefore, in particular, it's bounded in its domain. So if it's bounded in its domain, I can extend it to its closure. So extends it to its closure. Extend u hat to h by continuity. Okay, let's go into steps. Extend u hat to u tilde that goes from the closure of the range of modulus of A into the Hilbert space by continuity. So from that, I know that the norm of u tilde of x is equal to the norm of x for all x in the closure of the range of modulus of A. And define u as an operator. I can just use the orthogonal decomposition of A, oops. And I can just take the orthogonal sum with the range orthogonal. into the Hilbert space, and what it does, it gets something of the form x plus y, and just associate uh, u tilde of x. Yeah, so basically it gives zero into the orthogonal of the range of the modulus of A. And that's exactly what tells what is the initial and final space. Yeah, so that's here you see that U vanishes into uh, into the range of A, which is precise, or sorry, into this space, which is precisely the orthogonal of the kernel. Yeah, so you see that the range of modulus of A orthogonal is the kernel of A. I'm making that my U vanishes into that space, which is consistent. And from that, from definition, U is a partial isometry because it preserves the norm in between two spaces. Yeah, so that's basically from the closure of the range of A into the range of A. Yeah, so it goes from the closure of the range of modulus of A, which is equal to the range of A star. Yeah, so remember, and it goes to the range of A by the very definition. Yeah, so that's is a partial isometry. And the way we define it, it's we have this definition. Yeah, so that's or have this formula holds. Yeah, so that's basically tells us that we can write a closed operator as a product of a positive one, namely the modulus of the operator, so the square root of the A star A, and some partial isometry. In particular, if the range of A is the whole space, yeah, so it's so basically if it's invertible, even though as an unbounded operator invertible, then U has to be unitary, yeah, because it has to define. So if the range of modulus of A is the whole space, yeah, which means also that the range of A is the whole space, then this closure will be the whole Hilbert space, which means it will be a norm preserving operator defined from the whole space into the whole space. Yeah, so that's the situation when A is invertible. And therefore U will be a unitary. Yeah, so it's a partial has exactly to do with the fact that A do not need to have a closed, sorry, a dense range. Okay, so that's basically how the idea goes. Yeah, so now I have basically some complex structure for closed operators. Okay, so I have the star represents the complex conjugation. I have real and imaginary parts, and I also have a polar decomposition. So somehow closed operators are not so different from complex numbers, apart from the fact that things will get really strange very soon. So for now, allow me to take this last 30 minutes to kind of set the type of framework we are interested in and to show some interesting result um, that will be kind of like a basis for many of our constructions. So here, physics really will appear for the first time, or at least some physics motivation. So what I want you to know for now is that like by describing physics or quantum physics, we are interested into two types, two types of data, namely observables and states. Yeah, so this is true from the very beginning of quantum theory. If you look to the works of Heisenberg, Jordan and Heisenberg, Born and Jordan, from the very beginning, the idea of observables as some matrices show up and also the states. Yeah, so that states, in fact, since Bohr, the idea of states quite relevant, and matrix mechanics constructs this concept as these transition probabilities between states. Okay, so this is kind of like a foundational. We cannot really start talking about quantum mechanics without talking about these two things. And we need to mathematically, maybe we have some questions. Let's just see some. For some reason, my chat is not showing up the messages. I have to say, I try to open the chat and I just get a blank, like a window, which means I cannot really see. I get like a message saying that I had two new messages, but I cannot really see any of the messages. So if you have a question, please feel free to just open up your microphone and just speak up. Okay, so that's not okay. Okay, anytime any of you have any questions, okay, it's funny because I get another like red message in the chat, but every time I open the chat, I just get like a white screen and I cannot see any of the messages. So uh, I'm not sure how to deal with that because it's probably seems to be a problem with Zoom. Allow me to just try to stop.
Professor,
Yeah. Yes.
are you listening to me? Luis Diaz Jimenez is asking, do you define the square root via the Taylor series?
No, that's not the case because you cannot. So thank you for the person helping me that read up the message. Uh, no, it's a little bit more complicated than that. And the reason is because the square root uh, can only be defined by the series when the operator is bounded, or in a case you know that the series converge. And the reason is because if you want to say a series converges, it has to converge somehow. And this somehow means uh, usually norm. Yeah, so okay, I can define other ways of convergence that it can make sense, but usually it's more complicated. So I have to define it by using some more sophisticated tool, namely the functional calculus. Yeah, so functional calculus is usually, so let me open some for me. It's a very deep question, so very good one. Allow me to, instead of using the square root, allow me to start like motivating with another one, which is the exponential. Yeah, so you could say, what's e to a? Yeah, suppose a self-adjoint, and I want you to define what's that. And if you wanted to write that as the sum of a to the power n over n factorial, from 0 to infinity, you have a problem for the first term, yeah, because like if you say, oh, that's true, in particular, I would like to have that these partial sums, 0 to m of a n over n factorial, is a Cauchy sequence. But that does not go very well, even if you look to two successive terms, because, well, this is just one of these, so it's n plus 1 or m factorial. But if A is unbounded, this is in general infinity. Yeah, so that's even the first term is problematic. Yeah, so that's okay. It's not for all A's that it's infinity, but for big class of operators, if you take these powers, it will have to be self-adjoint, as it will have to be also infinity. So it cannot work this way. So what we do is to work with functional calculus. And functional calculus for unbounded operators, yeah, self-adjoint unbounded operators, rely a little on bounded ones. Namely, you have to look to a Taylor, a Cayley transform. So what's the Cayley transform? So it's the, I may get the signs wrong. Let's just see. I think it's minus z plus I. Yeah, so this is a map that transforms the real line, yeah, into the circle, into the complex number, just avoiding the point 1. Yeah, so let me see if I'm correct. So when z goes to infinity in modulus, it goes to 1. Yeah, so it's the point that's out. Yeah. So basically what you do is you take your operator, the unbounded operator A, which is self-adjoint. So the spectrum is in the real line. And then you look to this operator. Okay, maybe just allow me to, for avoiding confusions, they commute, and what you have to prove is that this is a bounded operator that does not have one into the spectrum. And in fact, there is a bijection between these two sets. Yeah, so this is a unitary operator, unitary not having one in the point spectrum, in the point spectrum. That means I transformed my problem of unbounded operators when the spectrum is in the real line into looking to operators such that the spectrum is in the unitary, like the unitary circle, avoiding the point 1 as a point, yeah, it's an eigenvalue. And in this circle, I can look to spectral calculus for normal operators, or functional calculus for normal operators. Yeah, because well, in particular, it is unitary. So when I take the square root, I'm using what I know about. So I know that the square root is well defined in the circle without that one point. Yeah, so that's important to remove this one point. Otherwise, I cannot define one good branch of the square root. And so I take the square root of this operator with the bounded one using functional calculus. And then I go back with the inverse Cayley transform. Yeah, so I can go back. So if I call this a function c, I have the function c minus 1, which takes a point. I will have to remember, but I think it's I that multiplies z. Oh, sorry, r. I have r minus 1, so in here should be a plus 1. So I'm doing that like basically using my memory, so I haven't done the calculation, but I think that's the correct inverse. So you can go back and forth using functional calculus from self-adjoint operators, which are unbounded, meaning the spectrum is the whole real line. From that, you can map into a unitary operator, or at least an operator such that the spectrum lives into the unitary circle, avoiding one as a point spectrum. In that, I have a branch of the square root. I take the square root and I map it back. That's usually how you do for dealing with unbounded operators. And it's a tricky that was invented by von Neumann. So I hope it answers, but it's much more delicate than just taking the Taylor series. So the person that read the first message could also read the others because still can't see the map. Ah, no, now it went through. Okay, so the Taylor series, and then what's the second one? Yeah. Modulus of is defined by applying the spectrum theorem to. Oh, yes. Okay, so it's Pedro just gave the technical answer that I was explaining. Yeah, so it's, as I mentioned, it is using well, either the spectral theorem or the functional calculus for unbounded self-adjoint operators. In this case, it's even positive. Yeah, so A star A is a positive, which means you can take a square root, but it has to be something more sophisticated. So Taylor series simply don't work because of what I'm mentioning here. Yeah, so there is well, basically you have a lot of infinities in every term. Did it answer the question? Yeah, perfect. Um, okay, so let me try to go. Yes. Okay, so back to some more so to the idea of to the general framework of physics. Uh, if we're talking about quantum physics, we do need at least two types of objects, namely observables and states. So for observables, what's my wish list? I want to have some algebra structure. I want to talk about the stars. Yeah. So up to now, I basically talk about unbounded, closed, self-adjoint operators into a Hilbert space, and I never said why. So that was very much physics. Oh, sorry, very much mathematics. So no intuition. I just throw you some facts, mathematical facts. Uh, Now I'm basically start telling you why I want to have uh, those facts. So in quantum physics, we want to talk about like observables, and for that I need to have some algebra structure. I will also require some involution, which is my adjoint. So I will briefly tell you what an involution. So involution is an operation such that the square is equal to the identity, meaning A star star is equal to A. Again, I'm thinking about bounded operators for now. Uh, Moreover, it's antilinear. Yeah, so you have A plus lambda B star. It's A star plus lambda bar B star. And it reverses order. Yeah, so if you have A, B star, it's B star, A star. Again, here, everything bounded. And just to tell you why I'm doing everything bounded, because when we are dealing with unbounded operators, they are kind of like related to bounded ones. Yeah, so we are going to talk about unbounded operators which are affiliated to some von Neumann algebra. So when I talk about an unbounded operator, I can kind of using spectral theorem to cut this operator, in particular the self-adjoint ones, to cut the operator to some bounded ones by just looking to some bounded set of the spectrum. And I can reobtain the operator just by integrating over the spectrum, and basically meaning I can somehow obtain the operator by the bounded ones back. Yeah, so that's why bounded operators are so important, but they are not the only thing. Okay, another thing that I will require, and that's basically leaving here, is the spectral theorem. And I will require some topology. Yeah, so I want to say uh, states are operators are converging. Uh, Basically, I will need a norm. On the other hand, for state, well, first I should see them as expected values. Expected values of observables. They should be compatible with the structure of a vector space, just, well, basically because the algebra structure is in there. So compatible with, oops, with the vector space structure, sure, of observables. And well, this is again part of the probabilistic interpretation. I want to be positive and normalize it. Yeah, so basically I'm interpreting it as expected values. And part of that is, for example, if I have some operator such that the spectrum has only positive values, I hope that the expected value of this observable will be positive. Yeah, so here I'm saying is like states should be positive linear functionals on the space of observables. Okay. Uh, and for that, what I need is precisely in so the notion of a C-star algebra, or more specifically, von Neumann algebra. Okay, not all physical models require a von Neumann algebra, but many of them require uh, uh, well, von Neumann algebras, but all of them I would say require C-star algebras at least. So what is a C-star algebra? So it is uh, well, it's basically it's a set as everything in mathematics basically with some operations, namely it must have a sum, um, a multiplication. Yeah, so I want to sum up my operators. I can multiply two operators, and it's also a scalar multiplication. Yeah, so it is a vector space with the field. When you consider the sum and the scalar multiplication, you also have the product that transforms it into an algebra. In addition, you have a star, yeah, so it's an involution which satisfies the properties I wrote above. In addition, it has a topology, which means it has a norm, and this norm must satisfy submultiplicativity, yeah, so that's the norm of A times B should be less or equal than the norm of A times the norm of B. It should be complete, yeah, so it should be a Banach algebra. So as a vector space, it's a complete vector space, meaning a Banach space. And last, and quite the opposite of least, yeah, so maybe the most important property of a C-star algebra, it's the so-called C-star property that tells you that the norm of A star A is equal to the norm of A squared. I haven't wrote down all the properties because we are mostly looking into what I will call concrete C-star algebras, and I will not talk about that anymore. So I just mentioned all these properties just to say, oh, it's basically an abstract structure, but having a C-star algebra and one state which is faithful and normal, which always exists, in fact, allows us to see a C-star algebra as just a sub-algebra of B of H, which is closed, in the norm. Yeah, so basically I say with the abstract structure that I just well describe it to you, I can find some Hilbert space. H will depend on some well state, yeah, that's basically hiding. Um, but then I can construct op some some structure, some bounded the set of the bounded operators on this Hilbert space that's constructed using the algebra A turns out to be basically telling us that all the C-star algebras are of the form some closed subalgebra of the bounded operators of some Hilbert space. So this is called the GNS. So here I'm using the GNS representation theorem. GNS. Just to tell you, I will work just with this more concrete version of the theory. And Okay, so now we have this basically version of like how or where mathematically lives my quantum system. Yeah, so basically the observables should form a C-star algebra. I will also look to von Neumann algebras. And for me, a von Neumann algebra M, and in here I can use many ways of defining just for like saving some times, save some time, is that, well, it's a C-star algebra that is also, and then I can use many topologies, but I can say it's weakly closed. So what is weakly closed is weakly closed in the weak topology. I could also say uh, equivalently that it's the same thing as is in the strong topology. Strongly closed. And what are those topologies? So that's why it's much easier to talk in particular about von Neumann algebras when they are represented in some B of H. They are nothing but, um, well, basically the topology. So the strong topology means I say that AN converges to A if and only if AN of X converges to A of X for all X in the space. And here I'm looking to Hilbert space. And weakly, oops, that means that if you take functionals, yeah, so if you take y of AN, oops, y of A n x converge to y of a n x for all x. Also here strongly, here weakly, and y in the Hilbert space. Yeah, so they are not equivalent topologies, but in this situation they are the same. And the celebrated von Neumann theorem tells us that M is a von Neumann algebra if and only if M is equal to its double commutant. So what's the commutant? So M prime is equal to all the operators in B of H, such that the commutator between A and B is equal to 0 for all B in the von Neumann algebras. Yeah, so it's basically all the bounded operators that commutes with everything in the von Neumann algebra. Okay, so that's kind of the minimum setup I would have to describe in my quantum system. So one thing that, well, that I'm basically missing if I say, okay, that's quantum physics, but what if I wanted to talk about algebraic quantum field theory, which will be, in fact, what is kind of behind my interests into these fundamental algebras. Not only, I can also be interested in just quantum mechanics without talking about quantum field theories. But if you want to talk about algebraic quantum field theory, you want to talk about the space-time kind of like influence in your physical system. And allow me to just mention some desiderata that I will use tomorrow to start with Heschlida. Maybe it's even better because then I can start defining standard subspaces from the motivation. So basically what we want, is a map that I will call, let's see, I have a name in my notes. No. So I will take basically Minkowski spacetime. So we'll call in here the dimension is arbitrary. Yeah, okay, I can think about like just one time, but many dimensions. And for all regions, or in particular all open regions, so sometimes you have some extra assumptions, but I want to associate some algebra, which could be a C-star or a von Neumann, depending on the type of system that I'm looking, that lives into some bounded operators. Now they are all live into the bounded operators of some Hilbert space, satisfying some properties. And the properties I wish to have are, well, there are several, so that will not be an exhaustive list, but let's start with the most like natural ones that I hope nobody will complain about, and I can even go with the others tomorrow. But if I have two regions, then the algebras should be also included. Yeah, so it's, here the intuition are I'm looking to local nets of von Neumann algebras, meaning for every region O, I want to assign the observables or the C-star algebra that contains all the observables within region O. Yeah, so here I'm saying that if you have one region contained into the other, everything that you can measure into the smaller region can also be measured in the bigger one, which is, I hope, very intuitive. That's called isotony. Then I will have some other one that's more up to debate, but that's locality or Einstein's locality. That's it goes for several names. But here, the first times a second prime shows up, which is this O2 prime, meaning the causal complement. Yeah, so it's two regions are causally separated. Then the algebras should commute, which means that the algebra of the region O1 should live not in the region O2, but in the commutant of the region O2. So here again, I ask for forgiveness for using prime for very many different things, but I hope the definition is clear by the context. Yeah, so for a region of space-time, prime is the causal complement. For an algebra, prime is the commutant. Another prime will show up, maybe even a fourth. Okay, so another thing that I wish to have is basically a representation or like a good behavior with respect to the Poincare group or to the group of symmetry more generally, which means that for every um, element of the proper orthogonal Poincare group, I will have a representation as a unitary operator. And if I take my region O and multiply by my unitary, yeah, so basically conjugate my algebra, well, that will be the algebra of the transformed region as soon as I take the Poincare proper orthogonals. Yeah, so that's covariance, so nothing too surprising, I hope. Okay, now I am going to be a little bit more specific and I will talk about the vacuum representation. And I'm not sure, so maybe Rafael can tell me if I can go 2 minutes more or the other course will start soon after or have already started even. Okay,
Well, like a
maybe.
real classroom, we are kind of stretched for time, but it's okay. Please complete 2 minutes. We can start 2 minutes late. That's not a problem.
Okay. So we assume the vacuum representation, meaning there exists a vector that I will call omega, which will I think about as the vacuum. There could be other okay, there is other interpretations and the same thing is true, but here's my interpretation is omega is the vacuum, meaning it's a vector which is invariant by the action of the Poincare group for all G into the proper orthogonal Poincare group. And for this one particular vector, if I take the algebra for the whole space acting to this vector, and here notice that it's non-local. Yeah, I'm taking the whole space. Yeah, so the algebra associated to the whole Minkowski space, and I act it into this vacuum vector. It gives something which is dense in the Hilbert space. Yeah, so that's basically I'm saying, well, whatever state exists, it should have been created from the vacuum. Yeah. And the last, well, okay, have two last, but I will stop with this one. I want to have a spectrum condition. It should be a spectrum condition on the generators of space-time translations, which basically hopefully says that particles have positive energy. It cannot travel faster than light. In particular, I can say, for example, of course, it depends a little bit. For example, energy is positive. Yeah, so the Hamiltonian has positive energy. Yes, for the vacuum. Yeah, so I'm basically looking to the vacuum representation. Okay, so I will restart tomorrow from this list, and I will add one last condition called weak additivity, and then show Heschlida, and from that it's natural to start introducing standard subspaces and natural in modular theory basically will follow. So I apologize for the person coming after me for my 5 minutes delay, but I will stop here.